Hello friends, welcome back to another session of DBMS. Today I'm going to discuss about ARIES algorithm for recovery and isolation, exploiting semantics. It is a database recovery and concurrency control algorithm in DBMS that ensures reliability and efficient transaction recovery after a system failure. ARIES algorithm was developed in 1992 by C. Mohan, who is from Indian origin, and IBM researchers at the IBM. ARIES is widely used in DBMS to maintain acid properties. Acid properties are the transaction properties, atomicity, consistency, isolation, and durability. So ARIES is widely used in DBMS to maintain the transaction with these properties. ARIES is used in IBM DB2, Microsoft SQL Server, and PostgreSQL. uh, Oracle do not use array. It uses redo logs, undo segments, and SCN, which is like system change numbers instead of arrays. Today, there we have cloud and distributed databases, and these databases uses MVCC, which is like multi-version concurrency control and distributed wall and etc. Because the reason is ARIES was designed for disk-based databases, but today the modern databases are cloud and distributed, so they don't use ARIES directly. They use some hybrid versions of ARIES combining with some other algorithms and so on, because the modern databases use in-memory processing and so on. Okay, so ARIES is still, it is a state-of-the-art algorithm, which means that the algorithm is still relevant today. Okay, so we need ARIES algorithm, as I already mentioned, that it is used for recovery, so handles crash recovery efficiently, and it supports write-ahead logging, which is WAL, and uses physiological logging, which is hybrid of physical and logical logging, and supports fine-grained logging, which is row-level logging. So these are all the benefits that ARIES gives us, and that's the reason why the crash recovery happens in a seamless manner. ARIES uses the concept of steal and no force buffer management policies. So the reason for this is to optimize system performance and ensure durability. So what is steal? Steal is like before the transactions commit itself, like we'll write them onto the stable storage, like which is onto the disk. The reason for this is because we want to prevent buffer overflow if the system runs out of memory. So dirty pages, what is meant by dirty pages? Dirty pages are the pages which are like the uncommitted transactions. So those are considered to be dirty pages, and these dirty pages are written to the disk. Okay, so why we are doing it without committing is because we don't want the memory to overflow, the buffer overflow. Or steal prevents memory limitations from blocking new transactions if the transactions are very long. Okay, so then maybe the modified pages may not fit in the entire memory. So in that case, what we'll do is these uncommitted transactions, we'll write them onto the disk. Okay, but they are the dirty pages, but ARIES has a technique to recover from such kind of dirty pages. So what will happen without steal? Without steal, such transactions would be inefficient. So say for example, T1 is the transaction ID which updates account A with like debiting 500 from account A. Before T1 commits, the buffer is full. So what happens is the dirty page is written to the disk. So the T1 updating the account A, debiting it with 500 rupees is updated to the disk before it commits itself. Now say T1 crashes. Since the change is already on the disk, undo is required. So we need to undo because there is a system crash. So ARIES scans the logs and restores A to its previous value. Still needs undo during crash recovery. So what is no force policy? So the no force policy is like delaying writing committed transactions to the disk. Earlier, like in the steel, what we did is like we have written uncommitted transactions to the disk, but now in the no force policy, we are not forcing the committed transactions onto the disk. Okay, so this is because like we want to improve the performance by allowing batched writes. Okay, because we just want to reduce the disk IO operations, which can be a overhead in terms of performance. So instead of doing single writes onto the disk all the time, so what we do is we do batched writes. So helps in optimizing checkpointing and transaction commits. Okay, so what's the issue? If a crash occurs before pages are written, some committed changes might be missing. Okay, so this requires redo mechanism. So ARIES ensures all committed transactions are reapplied So transaction T2 deposits 500 into account B and commits. Okay, but the DBMS does not immediately write changes to the disk, say for example. So then what happens? The crash occurs. The redo phase is needed to reapply T2. So ARIES handles no force using redo phase. Okay, so as you can see in the steal phase, it needs undo during the crash recovery, and no force requires the redo phase. Okay, fine. So now we'll look at like various data structures used by ARIES. The first one is log sequence number, which is LSN, and write ahead log, which is WAL, and dirty page table, which is DPT, and transaction table, which is DT, and compensation log records, which is CLRs. Now we'll see each and everything in detail. So log sequence number LSN. So the definition of LSN is like it's a unique increasing identifier assigned to each log record. So say for example, in this particular figure, like you have T1, which is at which started early. Okay, right. So the sequence number of this LSN will be in increasing order. So based on the LSN, you can say like which transaction is older and which transaction is the new one. Okay, right. So T1 started. So when T1 started, we are giving LSN 100 over here. And for the next operation, like which is updating A's account by debiting 500 rupees, then the LSN is 110. So you can see that the number of LSN is increasing over here. So it's a unique increasing identifier assigned to each log record. And the purpose of this is helps in tracking operations for undo redo operations. So the LSN purpose is to track operations for undo redo and ensure proper ordering. So the key properties is like monotonically increasing, stored in log records and data pages, used for efficient redo and undo recovery. So this is how an LSN table will look like. So LSN and then transaction and the operation performed. Okay. What is meant by write ahead log, WAL? So a sequential log storing changes before they are written to the database. Okay. So whatever changes we are doing, all the changes are written into this particular WAL before they are written onto the stable storage. So this ensures durability and atomicity by maintaining a record of all changes. So what are the contents in WAL? So WAL contains LSN number and also the transaction ID and the operation details like insert or delete or update operation, and the before image and the after image. So the before image is like what is the state, what is the amount in A's account, and after image is what will happen to the A's accounts after the operation. Like it could be insert, delete, or update or whatever. So this is how a WAL looks like. So next is dirty page table. So a table tracking pages modified in memory, but not yet written to the disk. I already told you what is a dirty page. Speeds up recovery by avoiding unnecessary redo operations. So we have a table, right? So looking at the table, we'll know like which are written and which are not written. So what will be there in the dirty page table? So we'll have page ID and the recovery LSN. So what is rec LSN? Rec LSN is the recovery LSN, the smallest LSN of an update on this particular page used in redo phases. So this is how like the dirty page table looks like, the page ID and the recovery LSN. So next is the transaction table, which is also called as TT, a table tracking active transactions in the system. So helps in undoing uncommitted transactions during recovery. So what will be the contents of this transaction table? The transaction ID, last LSN, and the status of it. Okay, so what is the last LSN, which is for T1, the last LSN is 120 and the status is committed. And then for T2, the last LSN is 140 and then it is active. So it will maintain the status of like active, committed, and aborted transactions, and it will also record the last LSN of a particular transaction. So we already have seen like how a transaction is kept. So this is the transaction. Last LSN of the transaction will be like 120. For T1, the last recorded transaction is 120 and the status of this is commit, right? So this is what it will be maintaining in this particular transaction table. For T1, it is 120 and it is committed, and T2, it is 140 and it is active. So the next data structure is compensation log records, so CLRs. So special log records generated when undo is performed, ensures idempotent undo, prevents repeated rollbacks. So what are the contents in the CLRs? In the CLRs, like we'll be having the LSN and then the transaction ID and also undoing LSN and then the action. Like what is the action like we have to do? It's a restore of A, where A plus and then 200 need to be added into A's account. This is how the CLRs look like. So, what are the data structures that are used for redo operation and the data structures that are used for undo operation? So, log sequence number, write ahead log and dirty page table and transaction table and log file, all these are used for the redo operation. So, log file is a secondary data structure, but the primary ones are the five that I have listed. Then for the undo operation, the data structures that we'll be using is log sequence number, compensation log records, transaction table, and log file and undo list. Log file and undo list are the secondary data structures that we use for these operations. So these are all the data structures that are used for redo and undo operations. Now let us look at the various phases in the ARIES algorithm. The first phase is like analysis phase and the next redo and the undo phase. So there are altogether three phases in ARIES algorithm. So before starting with the analysis phase, let us try to understand what is meant by a checkpoint in DBMS. So coming to the checkpoint, a checkpoint is a mechanism in a database management system used to reduce recovery time after a system crash. It records the current state of the database by saving key system data structures such as transaction table and dirty page table to stable storage. After a failure, the recovery process starts from the last checkpoint instead of scanning the entire log, making recovery more efficient. So there will be a checkpoint from where like the recovery process will start. So save point is different from checkpoint. Save point is like where we roll back to the previous save point and all that. Checkpoint is from where we start the recovery process. So that's the difference between the save point and checkpoint. So when the recovery manager is invoked after a crash, restart proceeds in these three phases. Okay, right. From the checkpoint, the three phases will start. So what is analysis phase in ARIES algorithm? So coming to the analysis phase starts from the last checkpoint. Okay, and scans forward in the log. So from the checkpoint, it keeps scanning all the logs to collect necessary information for redo and undo information. So what will be the outcome of the analysis phase is it will sort out the transactions which are committed, which are for redo operation and which are for undo operation and so on. So it will initialize the transaction table and the dirty page table, and then it scans the log from the checkpoint to the end, processing each and every log record. And for each log record, it will update the transaction table. And I already have shown you the transaction table. So the transaction table will look like this. So the transaction ID and the last LSN and the status of it, like whether committed active or not. So it will keep all this information in the transaction table from the checkpoint, and then it updates the dirty page table for page modification. So if the page modification is found and it's not in the DPT, it will add it into the recovery LSN. Identify the starting LSN for redo. The minimum recovery LSN in DPT determines the redo starting point. Identify transactions that were active at crash time. So any transactions without a commit or abort record is considered uncommitted and will be undone. So what will be the output of the analysis phase is that the transaction table is updated with the active, committed, aborted transactions, and the updated dirty page table, dirty pages and their recovery LSNs are being updated, and starting point for redo and list of transactions for undo operations. So these are all the outcome of the analysis phase. Once the analysis phase is over, then the system moves to the redo phase. So what happens in the redo phase? So in the redo phase, like it ensures that all committed changes are applied to the database. So the steps in the redo phase involves these: find the starting point, start from the smallest recovery LSN in the dirty page table. This ensures we redo only necessary operations. Scan the log forward from the recovery LSN, read each log entry and check if it needs to be redone. For each log record, check if the affected page needs redo. If page ID exists in DPT, continue. If LSN is greater than or equal to page LSN on disk, redo is needed. Otherwise, skip because it's already applied. Reapply the operations if necessary. Redo the operations using the log entry. Move to the next log entry and repeat. Redo completes when all necessary changes are applied. I'll show this with the table example. So this is the redo phase in the ARIES. Like log sequence number is considered LSN, unique ID for each log entry. Page LSN is like on disk Okay, so the most recent LSN applied to the page and stored on disk. So that we'll call it as page LSN. So if page LSN on disk is greater than or equal to LSN, which is like the log record, so this means that the change is already written to the disk. So no need to redo this operation. Okay, fine. So if you just look at the LSN, so these are the LSNs of various transactions, and this is the transaction ID, and then this is the operations that we are performing in each and every transaction. Then this is the page ID, and this is the page LSN on disk. Okay, and the redo needed or not, like we are deciding here. So if, like for example, for transaction T1, the LSN is 100. So we are checking the condition, page LSN is 95. So 95 is less than LSN, which is 100. Yes, this is true. So we need a redo operation. So here we are marking that yes, we need a redo operation. So for the next transaction, the LSN is 102 and page LSN, which is like the LSN on the disk, is 102. So page LSN is equal to LSN. So which is like it has been written onto the disk. So no need to redo that operation because already it has been written onto the disk. So which is like skip operation. So we don't need to do anything. So the next is like LSN 104 for the transaction T1. So page LSN is 101, which is less than LSN, which is 104, which means that we haven't written anything onto the disk. So we have recent activity in the log itself. So we need to do a redo operation. So this is how the redo phase in ARIES works. So after the redo phase, the database is consistent with all committed transactions. So all the committed transactions which are not written onto the disk, we are redoing all those operations and writing everything onto the disk. So redo phase ensures that the database is consistent with all committed transactions. Uncommitted transactions will be undone in the undo phase. Okay, so now we are coming to the uncommitted transactions. So the undo phase applies each operation in reverse order and writes the CLRs for each action. If a crash happens again, ARIES can use the CLRs to avoid redoing undone actions. So you can see that here in this table. So as I have already told you that the operations, the undo phase applies each operation in reverse order. Okay, so reverse order. So as you can see that the LSNs are in reverse order, like the most recent first and then the oldest at the end and so on. So this is how it keeps them. So whenever it feels that the data is written onto the disk or it is undo operation is not needed, it will stop there. So from the reverse, it will keep on applying the undo operation, and wherever it feels like it is not needed, it will stop there. So that this is the transaction ID, and the operation is update A is equal to from 100 to 200. So A's account has been updated from 100 to 200. So we need to undo this operation. So we are keeping it as 100. So undo action has been performed. So A's account is set to 100. So CLR generated. So did you update in the compensation log records? Yes. Why we are updating in the compensation log record is that if again there is a crash, we won't be doing undo operation again. Okay, so because we'll be checking in the CLRs whether undo operation has been done or not. So in CLR, if undo operation is already done, we won't be doing that action again and again. So next is LSN 115. So transaction T2 and delete from orders. So what we are doing is we are reinserting the row because we have deleted some tuples in the database. So we'll be reinserting the rows and then CLR generated. Yes, it is generated, which is like just a status of whether we have undone or not. Okay, so CLRs will keep that track. Next is 110 and T1 insert into users. So we have inserted some data into the users, which is uncommitted, and we need to undo it. So whatever rows we have inserted, we'll be undoing all those, like deleting those rows. And CLR generated, yes, it is generated. And next for 105 transaction, which is T1, update B's account from 300 to 400. So we are taking it back to 300 and then CLR generated. Yes, it is generated. Okay, so this is how the undo phase in ARIES works. So from the table, what did we understand? Identify transaction to undo, then check the transaction table to find whether the transactions were active at the time of the crash, then process undo using the log sequence number, start from the highest LSN of each uncommitted transactions and move backward in the log. That's what I showed you in the table. Then write compensation log records. So why we are writing CLRs is for each undone operation, ARIES writes a CLR to track the rollback. So that CLR has a forward pointer to support repeating history in case of another crash. Apply the undo operation. So reverse the effects of the original action. So I showed you like how delete operation, insert operation has been undone. Update the transaction table. So if a transaction is fully undone, it is removed from the transaction table. Stop when all transactions are undone. Okay, continue until all uncommitted transactions have been rolled back. So this is what happens in the undo phase of ARIES. So before ARIES ends, what will happen is the committed transactions are redone and uncommitted transactions are undone. Okay, checkpoint is updated. So now we are updating the checkpoint to the consistent state, and system is consistent with the new checkpoint and ready for the normal operations. So all the uncommitted transactions are rolled back in the undone phase, and then CLRs are written to maintain crash consistency, and transaction table is updated, removing fully undone transactions. So all this happens before ARIES ends. So once ARIES ends, you can be sure that the database is in consistent state and is ready for the normal operations. I hope the ARIES recovery algorithm is clear to everybody. If you find this video helpful, like, share, and subscribe, and also comment in the comment section below. Thank you for watching.